Assalamu alaikum. I'm Dr. Rosina Chaudhary, your formal teacher of Plasma Physics 2. Today I'm going to facilitate you on plasma resistivity, which is another topic from the coursework of Plasma Physics 2. Well, you can find this topic from your chance book in the paragraph number 5.6 is about the collisions, and in paragraph number 5.6.1 of the chapter number 5, directly you can find the plasma resistivity topic. Well, when the plasma is very dense or the number density of the plasma particles is very high, then the collision or the resistivity term become very important. And if the plasma is fully ionized, I mean if it is composed of ions and electrons, then all the collisions are expected to be Coulomb collisions between the charged particles. However, we can have different type of collisions like the collision between two like particles, I mean anion collision or the electron-electron collisions, and the collision between two unlike particles like electron is going to be collide with the proton and vice versa. Now we consider if we consider two identical particle collisions, and if it is a head-on collision, then particle will emerge with their velocities reversed. They will be moving in the opposite direction, then simply interchange their orbits and the two guiding center remains in the same place. It means that in case of the two like particle collisions, the guiding center does not move, remain fixed. So diffusion is not very important for such collisions. The same is the case if the electron is going to be collide with some neutral atom. On the other hand, if two unlike particles collide, I mean if electron is going to be collide with the proton, then in this situation the particles will emerge with their velocities reverse. And since they must continue to gyrate about the lines of force in the proper sense, so in this situation, or I mean in case of the unlike particle collisions, the guiding center will not remain fixed anymore. They will move in the same direction, or it means that diffusion, the unlike particle collision give rise to the diffusion. For such diffuse plasma system, the collision, the resistivity or the frictional or the dissipative term become very important. Here is the fluid equation of motion, including the effects of the charge particle collisions. Here we suppose that the electron fluid is under the influence of electric and magnetic forces. P is the usual thermal, the gas pressure, and this is additional term PEI appearing due to the collision of electron fluid appearing due to the collision of electron fluid with the ions. And similarly here we can write the momentum equation for the ion fluid. Here we can see that this is the collisional term appearing due to the momentum gain of ion fluid caused by collision with the electron. Uh, Here we have defined PIE and PEI respectively as the momentum gain of the ion fluid caused by collision with the electron and vice versa. And since because this PEI is the momentum gain or the term appearing due to the collisional frequency, here we have defined this PEI as this is equal to the product of the mass of the electron. Since too many particles are concerned here, so we must take into account the number density as well. So PEI is equal to the product of mass of electron, the number density, and now obviously collisional frequency nu EI is the frequency of ion electron colliding with the ions, and multiply by the relative velocities of the two fluids, I mean electron and proton. And similarly, we can define PIE here as this is equal to the product of the mass of the proton, the number density of the protons, and the collisional frequency of ion fluid with the electrons. And here is the relative velocity of the two fluids. And since the collision is the con- con- we are considering here elastic collision, so we must take into account the conservation of momentum as well. It means that the momentum gain of the ion fluid caused by collision with the electron must be equal to the momentum gain of the electron fluid caused by collision with the ions, or in other word we can say that the sum of PIE plus PEI should be equal to 0, or the momentum overall momentum should remain conserved. All right, here we have defined two momentum expressions for the momentum gain of the fluid due to the collisional frequency. Now, as we are considering the charge particle collision, so along with this, on the other hand, along with this dissipative momentum gain, we must have another moment expression for the momentum, which is due to the Coulomb collisions. And in this case, while we can expect PEI to be proportional to the Coulomb force, you know that the Coulomb force is proportional to E square, the product of the two charges, and is proportional to the number density of electron as well as to the density of the scattering center, which is of course equal to the density of electron. And PEI, the Coulomb momentum, should also be proportional to the relative velocity of two fluids. So it means we can write this momentum expression of the due to the Coulomb collisions as this is directly proportional to the square of the charge, the number density of the particles, and the relative velocity of the two fluids. And if we remove the direct proportionality, a constant appear here, which is notated as here is notated as eta, and eta is the constant of proportionality is known as the plasma resistivity. It means now we are having two types of the momenta. One momentum gain is appearing due to the collisional or the dissipative term in the plasma system, and other is appearing due to the Coulomb forces. Here is the momentum appearing due to the Coulomb forces of attraction and repulsion between the charged particles. If we compare these two momenta, I mean if I compare PEI with the PEI shown in the previous slide, here with this PEI, if we compare these two momenta, then very easily we can cancel out some terms on both sides, and we will be left with as ME is mu EI is equal to eta and E square. This equation can be utilized to finally define the resistivity eta here, which turns out to be eta is equal to product of mass of electron, the collision of frequency of electron with the ions, and divided by the number density of the particles and square of the charge. Well, if we multiply this eta expression here on the numerator and the denominator with 4 pi, then we can express this eta or the resistivity in terms of the plasma frequency as well. You know that the plasma frequency is defined as 4 pi and E square over ME. So eta in this situation will turn out to be 4 pi nu EI over omega PE square. Here you can see that the resistivity varies directly with the frequency of the particles, and this is inverse function of the plasma, an inverse square function of the plasma frequency. Also you can use this expression to calculate the amount of collisional frequency of electron with the ions, which turns out to be equals to eta omega p e square 4 pi. So here eta, we have defined eta, the resistivity term. This resistivity become very important for dense system, or whenever we are concerned with the high density plasma systems, then this eta become very important in the future. Whenever we have to take into account the resistivity or the collisions in the system, we will be taking into account this eta or the resistivity term. Would We will be incorporating this term into our equations. Good luck with your learning.